Hello, everyone. This is Richard Wang. I'm a rising high school freshman, and today I'm glad to give a brief overview of my project applying vision transformers to Chinese character classification, assessing vision transformers' potential to outperform traditional convolutional neural networks on Chinese character-related tasks. My project stemmed from the question of how to recognize and reconstruct incomplete ancient Chinese hieroglyphs. This is important for archaeology. I believe that using stroke order is a good way to approach this problem. Even if parts of a character are missing, stroke order can help identify the general structure of that character. Recently, vision transformers have shown great results in computer vision. They are more suitable for recognizing large-scale patterns, and this coincides with my needs for stroke order. In this project, I compare VITs against traditional convolutional neural network models and examine whether VITs can surpass them. Let me briefly explain these models. Convolutional neural networks are traditional state-of-the-art deep learning models for computer vision. They extract local features through convolutions. On the right is the architecture of LeNet, which I have used for this project due to its simplicity. On the other hand, vision transformers use a transformer architecture, which is usually used in natural language processing. In the case of vision transformers, an image is cut into many patches. The advantage of the VIT lies in its ability to attend globally to the image patches, which can be thought of as words in the context of a sentence. For this project, I used a basic VIT called Simple VIT. On the right, you can see the vision transformer architecture. To test my ideas, I first ran an experiment on a small handpicked dataset and showed that Simple VIT can work with Chinese characters. Next, I obtained a larger dataset and found that Simple VIT does not do as well as a convolutional neural network. At this point, I looked through the source code of Simple VIT. I made some of my own adjustments, and I will call my modified version Simple VIT Conv for now. I added a convolution before the linear flattening of the patches. This prevents the loss of the two-dimensional structure of each of these patches. I also added overlap preprocessing. As you can see on the colored image on the lower right, each of the patches contains some of the pixels from its neighbors. I partially stemmed my ideas from existing VIT models like CVT and token-to-token VIT. Now for more experimentation. First, I changed the classification criterion from identifying font or script to a transposition. This is because I realized that font could be relying on details like serifs, which would defeat the purpose of using a structurally advantaged VIT. Simple VIT Conf is much better than the original one, but LeNet is still the best on average. I found some additional issues. The dataset was still too small and could be causing some overfitting. Also, the small image size was not ideal for cutting an image into many small patches. My goal was to see if Simple VIT Conf could achieve the highest performance. I also hypothesized that increasing the number of patches would result in better performance. I ran my final experiment using a much bigger dataset of larger images. I used 3 different experimental groups for Simple VIT Conf, varying the number of patches. These are my test accuracies. As can be seen, the original Simple VIT fails to learn anything, while the others all do fairly well. My predictions were supported. Simple VIT Conf with the greatest number of patches had an error rate over 3 times smaller compared to that of LeNet. There was also better performance with more patches. To conclude, my project tested the viability of using vision transformers for Chinese character-related tasks. After I made some adjustments, Simple VIT outperformed a convolutional neural network in a classification problem, and this shows promise for possible applications in the archaeological field. This brings us to future research. I plan on using a more complex training objective since classification is still well within the reach of CNNs. I also hope to use a more sophisticated VIT model like CVT. I have some ideas for further improving VIT and also hope to generalize it to unsupervised and generative versions. Here are some of my references. Above are the sources of code and datasets I used, and I also uploaded my own code to GitHub. Finally, I would like to sincerely thank Dr. Yang Xu for his supervision, support, and guidance throughout this project. Thank you for listening.